Hello, everyone, and welcome back. My name is Mr. Cobalt, and in this video, I'm going to be talking about the kinetics of radioactive decay. And here I'm going to be talking about first order kinetics. So let's get into this. So the first thing we need to realize is that radiation is all around us. It's in our environment. It's the background radiation that we are exposed to every single day. It's in the food we eat. It's in the earth, the ground that we're walking on. It's in the sun, the sunshine that we're getting. If you smoke, it's in there. You're getting a large dose of radioactive material when you breathe it into your lungs. That's why smoke is linked to cancer, and that's one reason. Also, it's basically everywhere, and so we're getting bombarded by radiation all the time. It's also due to the fact that, like, say, the ground, for example, and the air have radioactive elements, and these radioactive elements are decaying. So we saw earlier in another video that elements that are larger than 83 protons, elements or nuclei that have 84 protons or above, are going to be radioactive. We also have radioactive elements that are less than 83 protons. So again, some elements, smaller elements are going to be radioactive. Larger elements are radioactive, and they're constantly decaying and releasing particles. And so we're being bombarded by that. And so um, this decay is going to be a first order decay. So that means that all radioactive nuclei decay is going to be first order. The reason is because you've got the one atom, and so it's just dependent. The order, the rate of the decay just depends on the atoms that it has and whether that one atom is going to decay or not. So it just depends on the amount of the atoms you have, and so it's going to be first order. And so the rate law looks like this. So the rate is equal to K, which is our rate constant, multiplied by the number of nuclei. So you might remember from a previous video of mine where I went over rates of reaction rates. And so your first order reaction rate had a um, very similar equation where the rate is equal to the rate constant multiplied by the concentration of your reactant. So it only depended on the concentration of reactant. In this case, our reactant is the radioactive nuclei that's going to undergo the decay. So this is our rate law. As you notice, if K is large, then it's going to decay quickly. The rate is going to be very fast. So K is large, then it's going to decay quickly. If K is small, then the rate is going to be small and it's going to decay slowly. So that's our rate law. So how does this relate to half-life? Well, we got to remember what a half-life is. The half-life is the amount of time it takes for half of your original sample to be cut in half. It's for half of it to decay over time. And so when we're talking about nuclear decay, when we're talking about radioactive decay, we're talking about the parent nuclides that we start with. So here, the half-life is the time it takes for half of the parent nuclides in a sample to decay to the daughter nuclide. So how long does it take for half of it to decay and become daughter isotopes? Okay, so here, if you remember from a previous video, so this is the half-life for first order decay, for a first order reaction. And so here it's 0.693 divided by, again, the rate constant. So again, if the rate constant is large, meaning that it decays quickly, then this is going to be large. So that means that this is going to be small. The ratio is going to be small. So that means, excuse me, sorry about that. So again, if this is large, then that means that the half-life is going to be small. So short half-life means that it's going to be very active. Very active means that you're going to have a large number of decay events happening in that time. So here, if the rate constant is small, that means it decays more slowly. That means that this is going to be small. The smaller that the rate constant is, that means the larger the half-life. So you're going to have a longer half-life, and that means it's going to be less active, meaning less decay events over a particular period of time. So if we go over a couple of examples. So here, the first example is we have thorium-232. It's an alpha emitter, and the half-life is 14 billion years. So 14 billion years is the half-life. That means that if I start with a sample, it doesn't matter how big this sample is. If I start with any sample of thorium-232, it will take 14 billion years for half of that to disappear. So if I start with a kilogram of thorium-232, then after 14 billion years, I'll have half a kilogram. It doesn't matter. If I start with a gram of thorium-232, it'll take a billion years for half of that to decay, and I'll be left with a half a gram. So no matter what the original sample is, the half-life is always going to be the same. So 14 billion years for half of that original sample to decay. So my example here is if I start with 1 million atoms of thorium-232, then after one half-life of 14 billion years, then I'll end up with 1/2 of a million of the parent isotopes or atoms left over. So 1/2 of them decayed and became daughter isotopes. They decayed and became something else. So now I have 1/2 a million left. Now the 1/2 a million here is again going to be my new original sample. After another half-life, then I'll have half of that left. So 1/2 of a half is 1/4. So I have 1/4 of a million of my original sample left over from where I began. So I began here, and after 2 half-lives, I have 1/4 of a million atoms of my thorium-232 left over. So you'll notice that it doesn't go to 0 after 2 half-lives. It's not like half of it decays after 1 half-life, and then that rest of the half decays after the second half-life, and therefore I have 0. That's not the way it works. It's always half of the original sample that we are starting with at that particular half-life. So here we're starting with a million. 1/2 of a million is 1/2 a million. And so we end up with 1/2 a million after the first half-life. And then now this is what happens after another half-life. So now we're going to take a half of this. So half of this is going to decay after another half-life. So 14 billion years later, I end up with 1/4 of a million atoms left over from my original sample here. And then if I undergo another half-life, so I go with another 14 billion years, and now I'm going to have 1/8 of that million left. So, and then I'm going to take another half of this, which would be 1/16th, and then 1/32nd, and so on. So it's always going to be a half of the previous amount that I had. So what about this example here? So if I have Rn or radon-220 here, this has a half-life of 1 minute. So it's the same idea. So in this case, this is going to decay more quickly. So if I again start with 1 million of these atoms, after one half-life, which is a minute, I'm going to end up with 1/2 of a million left over. The other half decayed to whatever the daughter isotope is. And now after another half-life, this 1/2 a million will decay by half. And so then I'll be left with 1/4 and after another minute. And then after another minute, this 1/4 will decay in half. And so then I'll end up with 1/8 of a million and so on. So this is going to decay a lot faster than this because the half-lives are different. So what about a graph? So here I have a graph. Again, it's a sketch of a graph, but the important thing is when you're given a graph like this, I can graph out the half-life versus given that time is on the x-axis, time versus the number of atoms. So as time goes on, the number of atoms are decreasing steadily. And so if I'm given a graph like this, I can figure out what the half-life of my isotope is by looking at the graph. So I know that by definition, the half-life is what? The half-life is the amount of time it takes for half of the original sample to decay. Well, if I know what the original sample is, let's say 1,000,000, then all I need to do is find half of 1,000,000 on my graph and then go all the way to the line here, the graph here, and then go down to the time. So I go over from half of my original sample, whatever it is, here it's 1,000,000. I find the halfway mark. I go across until I hit my graph. And then once I hit the graph, I go down to the x-axis for the time. And that would give me my half-life for this particular isotope. And you could do that with any graph that you're given. You could always figure out what the half-life of a particular element is from the graph if they give you the graph. And it's that simple. That's it for this video. In my next video, I'm going to be talking about the integrated rate law and how you can use that to solve problems involving radioactive decay. If I'm giving a certain element or certain amount and I want to know, okay, so this is the amount of time it's been decaying, here's the half-life, how much of my sample is left after, say, 2 weeks or after 30 days or whatever the case may be. I will show you how to do that in my next video. I hope you enjoyed this video. If you enjoyed this video, if you learned something from this video, please, by all means, like the video. Hit that like button right there. Also, subscribe to my channel. Hit that notification bell. When you hit the notification bell, please hit all so you can be notified by all the videos I put out. Also, lastly, put a comment down in the comment section. Let me know what you think. If you have any questions, I'd love to hear them. Thanks for joining me. Have a great day.